Right, we've got an old S2 question from 2017. It's a normal approximation, a binomial normal approximation. 2 lines and 10 marks. Oh, there we go. So here we go. There, six-sided dice thrown n times. Right, brilliant. So we don't know what n is. Number of sixes is recorded using a normal approximation. Probably x is less than 50 is 0.0082. Correct 4 decimal places. And we've got to find the value then. So this is the binomial we're going to be working with. We've got n throws, just don't know what n is, and the probability each time is a sixth. We're going to be working with the probability x is less than 50, which is equivalent to less than or equal to 49 with a discrete distribution. We're approximating this to a normal. Now, in the formula book, it gives you what the mean and variance of a normal distribution of a binomial are. So we need those. So in here, we go for the mu in the normal is n times p, or n over 6. The variance np times 1 minus p, so it's n times a 6 times 5 6, which is 5n over 36. And as the variance, of course, we'll be using the square root of that because we need the standard deviation when we're working with the normal. And we're going to look at the probability that this normal distribution is less than 49.5, which corresponds to less than or equal to 49 for the discrete binomial distribution because of the continuity correction. And that's equal to 0.0082. So we've sort of got an upper of 49.5 and a lower of minus a million. But we're going to have to use the inverse norm because we don't know what the mean and the standard deviation are. So we're going to use the inverse normal to get the z value. So we put an area of 0.0082 in, a sigma of 1 and a mu of 0. That's the standard normal distribution. And that gives us a z value minus 2.39989. So it's 2.4 standard deviation to the left of the mean. Because this has been rounded off to 4 decimal places, I'm going to use minus 2.4, which is a far more convenient number than 2.39989. Because we've been looking for like a whole number answer, and this isn't going to give us one. So I'll take the z as minus 2.4. And then using our formula, now we could use this formula for the z, but I'm going to use this one, sort of the rearranged x equals. We used to use this a lot when we had to just use z values all the time, but now we've got the calculator. And we're sticking in the z value, we're going to get the x. So I'm going to use this version of it. It's just this rearranged. So I've got 49.5 for my x, and then the mu is at n over 6, and then minus 2.4 times the sigma, which is the square root of the variance, or root 5n over 6. If I rearrange this, multiplying by 6, I'll get n there, and I get 2.4 root 5 times the square root of n, and then 5 times 6 is 297. So this is a quadratic now in root n, and you can try and factorize it, but I wouldn't bother. I just whack it straight in the calculator, and you get root n is 9 root 5, which means that our n then is 9 root 5 all squared, which is 405.